Have you ever just stopped and wondered, why isn't the universe just a big, random fog of separate, lonely atoms? I mean, what's stopping everything from just flying apart? Well, the answer is one of the most fundamental forces in nature. And that's exactly what we're going to break down today, chemical bonding.
So, to really get to the bottom of this, we're going to tackle what you could call the fundamental mystery of matter. We're going to explore 4 key questions. First, why do atoms almost never exist alone? What is it that drives them to combine? Then, what are the rules of that partnership? And finally, why do the molecules they form have such specific, predictable shapes? Believe it or not, a single concept connects all of these, the chemical bond.
To solve this mystery, we have to start with the motive. And the motive here is a universal principle that governs, well, everything, from a ball rolling down a hill to the formation of entire galaxies. It's this relentless, universal drive towards lower energy and greater stability.
This seesaw right here illustrates the idea perfectly. Over on the left, you've got a high-energy system. It's kind of jittery, it's unstable, it's ready to change at a moment's notice. But on the right, you have a low-energy system. It's calm, it's ordered, it's stable. The huge takeaway here is that nature always favors the stable, low-energy side. So atoms form bonds for one main reason, to lower their overall energy and get to that stable state.
And that attractive force that makes all this stability possible? That's what we formally call a chemical bond. You can think of it as the fundamental glue that holds all of matter together, creating literally everything from the water in the oceans to the very air we breathe.
So how in the world did scientists crack this code? Well, like any good detective story, they found a huge clue by looking at the exception to the rule. And in the world of atoms, the big exceptions are the famously aloof, unreactive elements, the noble gases.
You see, noble gases like neon and argon are basically the only elements that are perfectly happy to exist as independent single atoms. They're inert, which is just a fancy way of saying they don't react with anything. And the reason why is all down to their electron architecture. Their outermost electron shell is completely full. For most, that's the perfect set of 8 outer electrons, what we call a stable octet. This full shell is pretty much the pinnacle of atomic stability.
This simple observation led to an absolutely revolutionary hypothesis. The idea was, what if the noble gases are the peak of stability? Then maybe, just maybe, all chemical bonding is simply an attempt by every other atom to achieve that same perfect electron configuration. In other words, they all want to be like the noble gases.
Okay, so let's meet our 2 detectives. In 1916, working completely independently of one another, 2 brilliant scientists, Kossel-Lewis over in America and Walter Koessel in Germany, both figured out how atoms pull this off. They took totally different paths, but they arrived at the exact same incredible conclusion.
We're going to start with Kossel-Lewis. He had this beautifully simple, almost visual idea. He pictured the atom as a kind of geometric puzzle. Lewis proposed what he called a cubical atom. He imagined the atom's core, that's the nucleus and all its inner electrons, which he called the kernel, sitting right at the center of a cube. Then the all-important outer shell electrons, the ones we called valence electrons, would sit at the 8 corners. In this model, a stable atom, like a noble gas, is simply a perfect cube with all 8 corners filled.
Now, to make this easier to work with, he created a really powerful notation that we still use today, Lewis symbols. It's super simple. Just the element symbol surrounded by dots, where each dot is a valence electron. This also helps us figure out something called group valence, which is basically just the number of bonds an atom usually wants to form. You just calculate it as either the number of dots or 8 minus the number of dots. All of a sudden, chemists had a simple vocabulary to visualize how atoms could fit together. Using this model, Lewis realized that atoms with these incomplete cubes could get to a full, stable octet in one of 2 ways. They could either transfer an electron from one atom to another, or they could share a pair of electrons, with each atom getting to count that shared pair toward its own stable set of 8.
Okay, now, at the exact same time, Walter Koessel was looking at this problem from a completely different angle. He kind of zoomed out from individual atoms and started looking at the big picture trends across the entire periodic table.
Koessel noticed this fascinating pattern at the far ends of the table. On the left side, you've got these highly electropositive alkali metals, like sodium. They've got a really weak hold on their outer electron and are just desperate to lose it. Then way over on the right, you have the highly electronegative halogens, like chlorine, which have a super strong pull and are desperate to gain just one more. And what's sitting right there between these 2 extremes? The perfectly stable noble gases.
He realized that this transfer of an electron actually creates charged particles, The atom that loses the electron becomes a positive ion, and the one that gains it becomes a negative ion. But look at the result. Both of these new ions now have the super-stable electron setup of a noble gas. Mission accomplished.
So what happens when you have a positive charge right next to a negative charge? Well, opposites attract, right? And in this case, they attract powerfully. Kossel defined this electrostatic pull between the brand new positive and negative ions as an electrovalent bond, which today we usually just call an ionic bond.
Let's look at the classic example. Good old table salt, sodium chloride. Sodium, or Na, has one lonely valence electron. Chlorine, Cl, has 7. So sodium gladly gives its electron over to chlorine. Boom. Sodium becomes a positive ion, Na+, with a stable configuration just like neon. And chlorine becomes a negative ion, Cl-, with a stable configuration just like argon. The attraction between them forms the bond. Simple as that.
And this whole principle works even when atoms have different needs. Take calcium. It has 2 valence electrons it really wants to get rid of. Fluorine, on the other hand, only needs 1. So what's the solution? Well, it's elegant. One calcium atom just gives its electrons to 2 separate fluorine atoms. The calcium becomes a doubly positive ion, Ca2+, and each fluorine becomes a negative ion, F-. Their mutual attraction creates the stable compound calcium fluoride, or CaF2.
So let's recap. On one hand, you've got Lewis thinking in terms of geometric cubes and dots. On the other, you've got Kossel looking at these big electrostatic forces and trends in the periodic table. They seem like really different approaches, so how do they fit together?
This table here sums it up beautifully. Lewis focused on the geometry of a single atom, using his cubical model and dot notation. Kossel focused on these huge macro trends, using a model of electronegativity and ions. But just look at that bottom line. They landed on the exact same unified conclusion. Atoms interact to get to that stable, noble gas configuration. And this just illustrates the complete picture perfectly. Lewis's dot structures give us the blueprint. It's the map of the valence electrons. Kossel's theory gives us the engine. That's the electrostatic attraction between ions that drives the whole process. But both paths lead to the one master rule. Forming a bond lowers a system's energy and creates stability.
This fundamental drive for stability, it isn't just some abstract chemistry concept. It is literally the blueprint for our entire universe. It's the reason water is a liquid, the reason rocks are solid, and the reason DNA can hold the code of life. It's an absolutely incredible example of cosmic complexity emerging from one very simple rule. So the question that leaves us with is this: what other complex systems all around us are built on such simple, fundamental rules?